Let's start with a scenario you probably remember. You buy a powerful computer, a fast processor, plenty of RAM. On paper, it is a beast. But when you hit the power button, you wait. And wait. Opening a browser feels sluggish. Installing updates takes forever. Why? Because for decades, the entire PC industry was being held hostage by one component. While processors were doubling in speed every 2 years according to Moore's law, storage barely changed. We were trying to run modern software on technology designed in the 1950s. Spinning disks, moving parts, mechanical delays, the hard disk drive. Today, we are going to perform an autopsy on this mechanical bottleneck. We will explain why read heads need aerodynamics, why older drives sound like a coffee grinder, and how solid-state drives replaced moving parts with pure electron flow. Story of how electrons defeated mechanics. This is Insight Lab. To understand the revolution, we must respect the dinosaur. The hard disk drive is actually a miracle of engineering. Inside a sealed metal box, you have platters made of glass or aluminum, coated with a thin magnetic layer. These platters spin at 7,200 revolutions per minute, 120 times every second. Reading your data is an actuator arm. Here is the terrifying part. The head at the end of that arm never touches the disk. It floats on a microscopic cushion of air created by the spinning platter. The gap between the head and the disk is just a few nanometers. To give you a sense of scale, if the read head were a Boeing 747, it would be flying 6 inches above the ground at 600 miles per hour. If it touches the ground, that is a head crash. Your data is physically scraped off the platter. But the real problem isn't danger, it's geometry. Hard drives use something called constant angular velocity. The outer track of the disk is longer than the inner track. That means in one rotation, the head reads more data on the outside than on the inside. A hard drive can be nearly twice as fast at the beginning of the disk as it is at the end. As your drive fills up, data is pushed inward, into slower and slower circles. Your computer creates its own traffic jam just by existing. And then there is fragmentation, the ultimate enemy of mechanics. Imagine a library where a single book is torn apart and its pages are scattered across random shelves. To read the book, the librarian, our actuator arm, must run to shelf A, then shelf Z, then shelf M. This is called seeking. The arm must physically accelerate, stop, and precisely settle over the correct track. This takes about 10 milliseconds. 10 milliseconds sounds fast, but to a processor running at 4 GHz, it's an eternity. Waiting 10 milliseconds for data is like a human waiting an entire week for a reply to a text message. During that time, your super-fast processor sits idle, doing absolutely nothing. The brain is waiting for the hands to move. For comparison, a modern hard drive accesses data in about 10 milliseconds. A modern NVMe SSD does it in under 1/10 of a millisecond. That is not a bit faster, that is around 100 times faster. So, we needed a change. Enter flash memory. But early solid-state drives had a dirty secret. We plugged them into the same cables we used for hard drives, SATA cables. SATA was designed for spinning metal, not for light-speed electronics. It was like connecting a fire hose to a garden tap. The memory was fast, the connection was not. So, engineers invented a new protocol, NVMe, Non-Volatile Memory Express. Instead of old cables, NVMe drives plug directly into the PCI Express lanes, the same high-speed highway used by your graphics card. This removed the speed limit. Suddenly, storage jumped from 500 megabytes per second to 7,000. Now, let's go microscopic. How does an SD store data without magnets? It uses floating gate transistors. Imagine a normal switch. Current flows, and that's a 1. No flow, that's a 0. But normal switches forget everything when the power is cut. So SSD cells add a trap, a conductive layer completely surrounded by an insulator. To write data, the controller fires a precise voltage pulse. Electrons are forced to tunnel through solid material. This is called Fowler-Nordheim tunneling, a quantum mechanical effect. Once electrons enter the trap, they cannot escape. The data is physically locked in, even if the drive sits in a drawer for years. But here's the catch. Writing is easy. Erasing is hard. You cannot overwrite a single cell. You must erase an entire block at once. It's like wanting to change one sentence on a whiteboard, but being forced to erase the entire board first. This process is slow and destructive. Every erase slightly damages the memory cell. Unlike hard drives, SSDs wear out. Modern controllers hide this from you, but your drive is quietly aging, one electron at a time. But speed is not just about electrons, it is about logistics. Imagine a massive warehouse filled with billions of boxes. That is your NAND flash. Now imagine you ask for one specific box. The worker, our controller, needs to know exactly which shelf and row that box is on. He needs a map. This is called the logical to physical translation table. Here is the secret that separates a $20 drive from a $100 one. DRAM cache. High-end drives have a dedicated memory chip right next to the controller. It works like the warehouse worker holding the map in his hands. Looking up a location is instant. Budget drives are often dram-less, sometimes borrowing a small piece of system memory instead. In those drives, the worker puts the map back on the shelf inside the warehouse. To find the file, the drive must first find the map, read it, and then go find the data. This is why cheap SSDs sometimes stutter when you move massive files. The controller is overwhelmed trying to manage logistics and data at the same time. And then we hit another wall: space. Shrinking transistors further made them unstable, so we stopped building wider. We started building taller. This is three-dimensional NAND. Instead of a flat city of memory cells, modern SSDs are skyscrapers. Manufacturers stack 100, 200 layers of memory vertically, all connected by microscopic channels. This is how terabytes of data fit inside a chip the size of a postage stamp. The verdict is clear. The hard drive had a good run. For over 70 years, it stored the world's knowledge. But physics has limits. Mechanical parts can only move so fast. Electronic signals move near the speed of light. So why do hard drives still exist? Because moving metal is slow. But it is cheap. And when you need to store the internet, cost still matters. But for your operating system, your apps, your time, if you are still booting from a spinning disk, you are not just waiting, you are fighting physics. And physics always wins. The choice is binary. Stay slow or subscribe and get faster. Join us for the next deep dive. This is Inside Lab.